All right, our next speaker, a man who needs no introduction because I already did it, Dr. Washer, back to the scene.
All right, so I'm Glenn Washer, as Rich said before, and I'm a professor at the University of Missouri is my primary role in life, but this, one of the things, we'll talk about advanced imaging today, and this is at the moment, a private concern or a commercialization of research previous. This is the outcome of some research, and so currently there's a company called ThermalStare. It's located in Northern Virginia. I was with Federal Highways at Turner Fairbank for 14 years, so it's with a colleague I used to work with when I was at Turner Fairbank. And it's commercializing some research that was done. Part of it was done is in pool fund that I had with states working on infrared thermography just generally. And the other part was through an SBIR with Federal Highways, which I'll mention again at the end, to develop a coatings technology, actually. And so this technology I'm going to talk about, which is a transient thermal imaging methodology, is an outgrowth of a coatings inspection technology that's intended to detect debonded coatings, like if you're metallizing, to find debonds between the metallizing and the subsurface, or just conventional coatings to find areas where there's delaminations and debonding of the coating from the surface, or there's corrosion underneath the surface. And so the way that works is it's got a light source, and you flash a little heat on the surface, and you watch the heat as it progresses from the coating into the substrate, the steel. And if those two things are adhered together, the heat goes right through. But if there's a debond there, or the adhesion is poor, the heat builds up on the center, basically. And so the whole test takes 10 seconds. You flash it, you watch it decay real quickly, and an image shows up. And so one of the people that used that technology, was developed originally on the SBIR with Federal Highways, is the Navy uses it on the surface of ships where the F-35 lands, because they metallize the surface. And so they use this technology to find debonds of the metallizing. And so we took that same idea, which was to flash heat on the surface and watch how the rate of change of that heat changed as it went into the material. So what if we took that and changed the time basis on it? Instead of doing it in 8 seconds, we do it over 8 hours or 12 hours or 24 hours. And instead of having a heat source, we just use the sun and the ambient temperature of the day. And we use the same algorithms, but now we're using it for a different purpose, to find damage inside of concrete. And so this system, which there's a patent was issued a couple of years ago for it, was an outgrowth of that. And so I'll be talking about that technology today. But it is marketed commercial, so you can buy it as a service, or we're currently working with one state that's going to rent a system for a long period of time, collect data, we'll analyze it for them for the purpose of doing epoxy injection on a really large bridge deck, so that they can locate exactly where defects are and fill them with epoxy. So we'll talk a little bit about that. The agenda here is, I'm not going to talk a lot about concrete damage modes, only to say what exactly this does. Because some comparisons with conventional IR, which is what you'd see on a drone, or which, if you bought an infrared camera, if you had a deck scan, infrared scan of your deck, that would be conventional IR, versus our transient IR, which we named Ultimate Time Domain, UTD, infrared, in which we collect data over 24 hours. We'll talk sort of exhaustively about that. This is the purpose of this technology is to find delamination, subsurface delaminations, and debonding in concrete. And so that's what it does. It talks about, the reason I sort of mentioned that is we got a lot of technologies floating around bridge decks. I know it gets pretty confusing. You got GPR, which is kind of measuring moisture in the deck and some sort of measurement of future damage maybe. And then you've got other technologies, and you got sounding that's detecting some shallow delaminations, and then you got a host of others. What this technology does is trying to find subsurface delaminations, cracks that are horizontal, that interrupt the flow of heat. Okay, so when the sun hits the bridge deck, the deck starts to heat up. If there's a subsurface defect, you get some change in the heat. Now, the way conventional infrared thermography looks at that and says, what is the difference in temperature between a sound and a delaminated area of concrete based on the surface temperature? What we do is we look at that image over 24 hours and say, what is the inertia of that? What is the rate of change of the temperature of the surface? And so it gives you some different results. We'll illustrate here what two primary things it does. It makes your technology a lot more reliable, which is the most important part to me, but also with some additional capabilities like finding very deep defects or penetrating through overlays, even asphalt overlays. And so we're really focused on existing damage. It's not going to tell you anything about damage that's going to happen next year. It's going to be whatever's there that day. As I mentioned before, the conventional IR, if you look at this sort of illustration, right, that subsurface delamination, it interrupts the heat flow through the deck. And so when the sun hits the deck, or even just the ambient temperature, there's less mass there to heat up. So above the delamination, it gets hot faster. At nighttime, just the opposite happens. It cools off faster. And so conventional infrared looks at that, takes a picture of that at one point in time, to see if there's a difference in temperature in the surface of the concrete. The problem is that's not very repeatable because this changes over the course of the day. You don't get the same results at 8 a.m. that you get at 10 a.m. that you get at noon. And so those times depend on the environmental conditions, but also on what type of defect you have. What is the depth of the flaw, for example? And because of that, the infrared's not even really very predictable. It's got good qualities, but it's got some relatively bad qualities. I think I got a slide here that sort of compares the two things in a minute. But, you know, I like to show this graph. This is from some previous research, and it's kind of hard sometimes to wrap your brain around this. But then the bottom on the black and gray is the thermal contrast. So that's the difference in temperature between a defective area concrete, one with a delamination, and a sound area over the course of 24 hours. So the horizontal axis here is actually 48 hours. The horizontal axis here is 48 hours. And this top blue line is the ambient temperatures over the course of 2 days. So it heats up in the day, it cools down at night, it heats up in the day. You notice that the heating up of the day, it has different slopes at different times. Those are relatively consistent. In the bottom, you see that those are three different flaws at three different depths, 1 inch, 2 inches, and 3 inches. The 1 inch defect shows up a lot better. The thermal contrast is higher as compared to 2 as compared to 3, and also the timing is different. The other thing is that, you know, at least 2 times a day there is no contrast. And so if you're there inspecting at that particular time, you don't see anything. And so the point is that this thermal contrast varies over the course of the day. When you have shallow delaminations, you'll see them if you're there at the right time. If you're not there at the right time, you don't see them. And so that sort of creates the problem. But a conventional IR scan looks like this. You've got a camera mounted on a vehicle somehow, and you go down the deck and you piece together the individual pictures, and that shows you temperature. The concept for IR-UTD is different. You're going to put a camera in place on the deck, up above the deck, so it sees a very large area, and we're going to take data constantly. You know, these days with computers, you can collect an awful lot of data pretty quickly, and so we collect gigabytes of data. We take a thermal image every 30 seconds, every minute over the course of a day, while the bridge is open to traffic. Because the cars are there, it seems like the traffic's a lot, but in the big picture of things, they're really a transient that just sort of crosses the image. We can remove them. I'll show it in a second what the data looks like over 24 hours. And so we're up above the deck. The deck's open to traffic, and we're collecting thermal images over 24 hours to 48 hours. And then we process that in order to find out where defects are. And so the concept is you've got lots of pictures. We take, you know, people, you don't really think about the fact that the thermal image is a pretty color picture, but every pixel in there is a value. Okay, given value, we've made it into color with some false color scheme, but there's an actual value there. So you take that pixel and you can track it over time and make calculations on it. So the difference here between what we do with the IR-UTD, which is this transient thermal method, is instead of capturing a single image, well, we capture lots of images over 24 hours. We don't calculate thermal contrast. We process the data with an advanced algorithm that gives you the thermal inertia, or the rate of change of that, to identify subsurface defects. Conventional is very sensitive to the environment. We're less sensitive to the environment. For one thing, we're collecting a lot more data, and so we can see things that are more subtle. You've got relatively limited depth because in conventional IR, we can see deeper. I'll show some examples of that. IR is almost totally ineffective through asphalt overlays, unless you're interested in the asphalt overlay itself, but in terms of concrete damage below it. And the reliability of conventional IR varies over the course of the day. It would depend on when you took the data. We show some results here that we're around 90 to 95% reliable based on physical sampling. So how do you mount this thing? You take it out, the camera weighs a couple of pounds. It can go up on a light pole, it can go up on we often use this parapet mount, which is shown in this upper left here. It just sort of bolts on. It takes about 50 minutes to set the system up, and it goes up on a mast about 35 feet above. And it's got a pan and tilt up there, so it's going to look around. It sees a length of around 240 feet and a width of around 80 feet. And so you can do a 5 or 6 lane bridge from one position all across all the lanes without disrupting traffic. The data we collect looks like this. This is infrared images on a bridge in Virginia over the course of 24 hours. In this case, our mast is, you can see the shadow of our mast as it crosses across the bridge over the course of the day and into the evening. And you can see some of the defects in that bridge just in this live. So this is a conventional infrared image, lots of them, collected every 30 seconds over 24 hours. Okay, so that's the data we take and we process. So our data, when it's processed, looks like this. That's the same deck you were just looking at. There's all the areas of subsurface delamination. You see a lot of them are, if you look at the bottom picture here, that's a regular photograph. You can see where the patches are on the deck. In the middle image there, we've circled the areas that are delaminations. You can see a lot of them are sort of around the patches. That's sort of a halo effect you get, that you patch one area and then you get deterioration around it. You see that in these thermal images. So just a sort of qualitative comparison. I show some quantitative comparisons here in a minute between, this is a deck in Oregon with an overlay, and the overlay's got lots of cracking in it. On the left is the conventional IR image at what would be the optimum time. You don't really see defects in that. On the right is the UTD image where you can see the cracks in the concrete overlay throughout. You can see how ubiquitous the cracking was, and you see areas that are defective circled in red there. And here's a core sample from one of those in that particular deck. It had a pretty thick overlay, 2.5-inch overlay on that, and it was very cracked up. The defects we're finding are down in the concrete beneath the overlay at a depth of 3 or 3.5 inches. And that's what we collect in data over 24 hours. So you see, like on the left, here's a close-up image. And one of the things that I think we sometimes have a hard time communicating, we try to communicate better, is that these images that are shown in the middle here, the top two, every pixel in that image is a piece of data, and it's a real piece of data gathered in the field. It's not, formulated through a lot of curve fitting and all this sort of colorization, all these other things. It's a piece of data from the field. I'll show you in a couple slides here what that data looks like if you just looked at one particular spot. There's some other things you can do with this that are kind of interesting. On the left here shows defects in the deck. This is one of the earlier tests we ran, but they're doing an epoxy injection on these defects. And so you see in the colorized image there, it says IRUTD image on it. You see the sort of red and blue areas that are the defect, the delamination. That red and blue is caused by the change in depth. So it's real deep in the middle, around 3 inches, a little 3.25 inches, and then it's growing towards the surface, and so that shows up as blue on the edges. And then you see a live image of someone on the deck actually doing the epoxy injection. So one of the ways this can be applied is to make an image of the deck, then you walk out and find where the defects are and stand on them and see yourself in the image. So that's kind of nice. There's also been doing more recently measurements through asphalt overlays, which is a very interesting thing. And this is, again, these images that are produced. The bottom is a photograph. The middle is with the defects circled in it, and the top is just what the IRUTD processed image looks like for a section of deck. The red defects in there are in the concrete, and the yellow defects are deep onto the asphalt. So because we collect this over time and it's an inertial measurement, we can tell information about what the depth is. And we're still working to perfect that, but we can tell shallow from deep anyway at the moment. And so we're still sort of working towards that. But we'll see in this, we'll show you some examples of this and of a box girder bridge of what the defects look like at different depths with the transient thermography. So this is a deck, and the reason I was interested in this, I thought would be interesting for this group, is here's a case where we're doing a bridge deck. It's got an overlay on it, but it's in a box girder, so it forms the top flange. And so the reason we were doing the imaging was not for a deck assessment as much as for a structural analysis of the box itself, because the top flange has got damage in it, and the consultant we were working with needed to know where this damage was so they could sample it and assess the bridge in terms of strength in order to identify what kind of rehab needed to be done on it. And so this system's set up here. We typically come out with a couple systems. It's a fairly long bridge. You can see it's curved there, and where the cameras were set up over the course of about a week, just take them up and put them down. Like I said, it takes about 50 minutes to put them up. It takes about 30 minutes to take them down. The bridge is open to traffic during the time the data is collected. And so here's what the delaminations in that deck looks like. The deck looks like it's fine. These are delaminations that are in the deck, either between the overlay and the structure itself or in the depth of the top flange of that box girder. So as I mentioned, so this data is very quantitative. And so these images, you see lots of color images these days, and they're processed somehow through, and some sort of surface is made. But these images aren't really processed. This is just, they are processed, but it's just the data from the field. And so we take the data over 24 hours, we process that and make an image that shows the slope over those rates and over those times, and that's what's produced into this image. And so in this image on the right is what the data looks like. If you look at this image on the left, there's a red line. It goes across two defects. The actual values that make that image are shown in the graph on the right. And so is the IRROC, that's rate of change. That's the rate of change at the surface at that point. And you see there's one of the defects has a lot higher amplitude than the second defect, and on there is a threshold where we can say, okay, things above here are a defect. And then the blue line that only goes halfway across that graph, that's over in an intact area of concrete. So that's what it would look like if it wasn't damaged. And so if you looked at the graph on the right, you get this big peak. That's the big delamination that shows up in white on the image. And then The second smaller peak is the second delamination that shows up on the image, and in between it's intact concrete. And so it's the red lines and the blue lines are the same there in between. If you compared that to, say, conventional IR, well, it depends on what time of day you looked at it. If you look at, like in the top here is that data from a UTD. The conventional IR, if you're looking at it at 10 a.m., you don't really see any result at all. That's on the bottom right. That gray band represents the noise level. In other words, what's the noise level in the ambient deck. Around 11 a.m., you start to see the bigger defect, but not the smaller defect. Then about 2:30 in the afternoon, if you happen to be doing your conventional IR imaging at that time, you would see both. At around noon, you'd see maybe the second one if you caught it. And so the point is that varies over the course of the day. And so if, depending on when, most states are using contractors to do this, depending on consultants, when their consultant goes out to do the bridge, it'll have a big impact on whether it's successful or not. And so we're doing something a little different in collecting the data for 24 hours, so we get all that conventional infrared image data, and then we process it to make it, give it more accuracy. Here's what the physical samples look like from that deck, where this white blob that I was showing you before, and what was causing these thermal anomalies in the inertial measurements of the deck, and what the depth are. So that smaller defect that showed up with a lower amplitude, well, it's because it's deeper in the concrete. It's around 3.5 inches deep. The other two are sort of, there's an overlay that's about 2.5 inches thick, and it's coming to bonded from the surface of the box girder that the measurements were made on. So we've done quite a bit of that over the recent years of taking physical samples to try to illustrate how this is performing from a reliability standpoint, because reliability is kind of the area that I do a lot of work in. Here's the results from that box girder bridge. There was 59 cores taken there. I think we missed 3 or 4. I've circled a couple in red on the right here. I'm pretty sure that 3.2 and 3.3 there, which I've drawn a red box around, I'm pretty sure the core is wrong in that one, because our data is very quantitative and there's sort of no escaping it. When it's those were defects. I think the guys taking the cores flipped the positions on those. I'm pretty sure of that. But given that we don't know that for sure, if you take that number, we got about 54 out of 59 cores gave the right result. And the second box I've circled in the right there that's a defect which you wouldn't hear with hammer sounding. At least we couldn't hear it with hammer sounding. But the core showed a defect, and our technology showed a defect. It was 6 inches deep inside the concrete, which is really really deep for an infrared measurement. On average, in these decks, on average, the depth of the flaws, the depth of the delaminations were on, I think, about 4.5 inches. And so that's quite deep to be able to make detection. Things that are more shallow than that, well, they're really easy to detect. And this data was collected probably not under optimum conditions. I think it was in the March of this year, not under the summer. We've done some of this previously with cores, with some bridges that are sort of around the Maryland area, Chesapeake Bay Bridge, Francis Scott Key Bridge, and the Oregon bridge out in Oregon. We get around 95% accuracy when we compare it with cores. And typically the way that works is we do the imaging, process the data, and then we tell the contractor or the state where to take cores, and they go out on their own and take the cores and then report back what the results are. And we normally take about a quarter of them in intact concrete and about 75% where there's supposed to be a defect in order to make that comparison, because you really have to, I mean, it's an old axiom in reliability, right? If you call everything a defect, well, you detected 100% of the defects. You also detected everything else, but you got 100% of the defects. So, and the other analogy they use for that is if a doctor's looking for a very rare disease that's only in 1% of people, and he says no one has it, well, he's 99% reliable, right? Because it's only the 1%. So you got to test both the defective area and the intact area, which we typically do in this coring. As I mentioned, this was an SBIR program with Federal Highways originally. And so it's won a couple of awards for that from the Small Business Administration, a Tibbetts Award, which we're pretty pleased about with that. It was awarded a patent a couple of years ago for the technology of doing this transient thermal imaging. We've done some other results with it as well. There's other things you can do with it. This is an example of a 500-foot tall tower where we're finding defects in the concrete up at about 500 feet from the ground without ever touching the tower, really. Just setting up a camera. And in fact, this was done with a conventional camera done by some people in the field, and then the data sent back to us, and we processed it with our algorithms to find these defects up this tower. And the other alternative to that is the way that other inspections was done was rock climbing the side of the tower and hit it with a hammer, which was pretty expensive and dangerous. So that's a good way. But this isn't a bridge, but there's lots of similar applications to bridges, abutment walls, piers out in the middle of a bay, things like that. The difference between this and conventional is we don't drive across and take one image. You put a camera there and you watch it over 24 hours. We kind of like to do 48 hours in case there's some bad weather, rain or something comes through, but you can do it in 24 hours or even less. You get improved detection, better reliability, which we think is an important role for that, and a larger depth. We've done quite a bit with cores. We showed you some of the results. It's around 90% reliable as compared to cores taken in structures. And so we think that this is an interesting technology. I mentioned this is kind of a commercialization of a research effort that we've had over a number of years. And so what we're doing with it currently is it's available as a service. We work with the Navy with the related technology on coatings, and we're working with some states in one case to rent equipment to them so they can collect the data. We do a lot of the data collection ourselves. My partner Paul and I, we're both PhDs. We go out in the field and put this camera up, which is probably not the best use of our time as PhDs, because anyone can set this system up. It's a little 3-pound camera. You put it up on a pole, and it does its thing. It's battery powered. Then you have data and you collect it. We also do the underside of bridge decks. We detect a lot of wildlife since we're there at night. Here's some raccoons out in the bridge. We were doing the underside of the bridge in this case. Since we're running 24 hours a day, we get a lot of this sort of wildlife pictures, and so they're fun. So I thought it'd be good for the end of the presentation. So, all right. So I'm at 22 minutes, Rich. Happy to answer any questions if anyone has any.
How much time and effort is involved in the processing of the data once you get it?
Yeah.
And is it very manual, or you have it automated and you push a button?
Yeah. It's pretty automated. It depends on the complexity of the application sometimes, because when things are deeper, there's very deep overlay. Sometimes it takes a little manipulation. But for most decks, you can do it in a couple minutes. Because it's all digital data, so you have an algorithm. So you say, this is my heating time, this is my cooling time, process of making me an image. Like the stuff that we did with in Iowa where they were doing epoxy injection, data was collected overnight, and then I processed in the morning about 3 minutes, and I gave it to them. Here's where the defects are, so they can go out on the deck. Now, some other stuff like the things in Oregon where there was a 3-inch overlay, high-density overlay, it was more. Because you sort of have to work your way through, okay, there's a big thick overlay here, and find the optimum times to calculate those measurements. So that's a little bit of but we're working on trying to automate all those to make those easier. It's very straightforward data process. There's not a lot of curve fitting or frequency sorting or anything else. The primary thing that's takes a little bit of time is identify, because the weather's always changing. It seems like a stupid thing to say, but obviously the weather's always changing. But the weather's always different, and so finding the periods of time when that are optimized to get that slope result takes a little bit of empirical fooling around, but it's relatively short